Welcome to the Lantern Light AI Newscast number 57. Your Brain on Science and Silicon. Made by Chris Morley in Boston on Saturday, May 30th, 2026 at 2:24 a.m. UTC. The brain is having a big moment in science today, with smarter neurostimulation devices expanding into new conditions. Wireless deep brain stimulation pushing forward at the University of Wisconsin, and researchers finding that stable brain networks are the key driver of cognitive outcomes. Meanwhile, MIT has cracked a cheaper method for extracting lithium. Computational neuroscience programs are pulling in record numbers of global applicants, and engineers are borrowing from brain architecture itself to patch the failure modes plaguing modern AI. Now, a story from the world of neural stimulation and therapeutic neurotech. Researchers and companies are pushing neurostimulation well beyond its established uses in chronic pain and hearing loss, with Cambridge, Massachusetts-based Cognito Therapeutics among the firms drawing significant attention. The company raised $73 million in a Series B round and has reported multiple positive study updates for its non-invasive spectrized system, which targets neurological conditions through electrical brain stimulation. A UNSW biomedical expert noted in February 2026 that next-generation smarter devices could transform medicine by offering more precise and responsive therapies. The field spans both implantable and surface-level devices, with regulators still working to establish consistent classification frameworks across the growing range of products. Here's a story making waves in research. Scientists at MIT have developed a new method for extracting lithium from rock that is cheaper and more environmentally friendly than techniques currently in use. Most consumer electronics rely on lithium-ion batteries, and demand for the metal has surged as the world moves toward electrification. The MIT team's approach targets the extraction stage, which has historically been one of the more costly and polluting parts of the supply chain. Details of the research were reported this week, though the technology would still need to be scaled up before it could be adopted by mining and battery manufacturing industries. And a notable item from the broader science and tech beat. A study published May 26th in Nature Communications found that stable brain network organization plays a more critical role in shaping cognitive outcomes than the dynamic shifts researchers have long focused on. Separately, research published May 25th in Nature Neuroscience used magnetoencephalography and eye tracking to show that when people look at natural scenes, how long they fixate on different areas is driven more by memory encoding than by visual complexity. Together, the two studies suggest that both large-scale network stability and memory processes shape how the brain handles perception and cognition. Researchers say the findings could influence how computational models of the brain are designed going forward. Now, a story from the world of neural stimulation and therapeutic neurotech. Researchers at the University of Wisconsin are advancing wireless deep brain stimulation technology, working to eliminate the external wires and chest-implanted pulse generators that current systems require. Traditional deep brain stimulation involves inserting electrodes into precise brain regions and connecting them to a pacemaker-like device in the chest, a setup that carries infection and hardware risks. The Wisconsin research aims to make the entire system fully wireless and implantable. Separately, closed-loop brain-computer interface systems, which automatically adjust stimulation based on real-time brain signals, are gaining traction among neurotech developers as a next step toward more personalized therapeutic devices. Now, a story from the world of computational neuroscience and cognitive architecture. International applications to computational neuroscience and cognitive architecture programs have risen steadily heading into the 2025 and 2026 academic cycles, with PhD opportunities in the Netherlands, the United States, the United Kingdom, and Australia, attracting particular interest. Researchers in these fields study how the brain processes information and how those principles can inform the design of intelligent systems. Programs typically combine neuroscience, mathematics, and computer science into a single research track. Prospective students are encouraged to check individual university portals directly, as application deadlines and funding availability vary significantly across institutions and countries. Now, a story from the world of computational neuroscience and cognitive architecture. A paper published on SSRN titled The Intelligence Gap proposes a 4-layer cognitive architecture modeled on the structure of the human brain as a way to address known failure modes in large language models. The design places the language model as a replaceable interface, sitting above 4 underlying layers, rather than treating it as the core reasoning system. The approach draws on principles from computational neuroscience, a field that studies how neural structures give rise to thought and behavior. Researchers in this space have been exploring whether brain-inspired system designs could make AI more reliable and interpretable than current architectures allow.
Today's program is brought to you by Lantern Light AI. Please note that Chris Morley is a seasoned software architect currently available for inquiries seeking help using AI to build, run, and maintain modern web applications, cloud systems, databases, streaming data pipelines, search engines, interactive 3D graphics, as well as other high-performance software services at scale. If the avatar or the newscast format interests you, and you would like to see something like this customized for your business use case, please email Chris Morley at chris.morley@lanternlight.ai. If you enjoyed this, like, subscribe, and share with your friends. More science, tech, and AI news coming soon. Thanks for watching.